My guest today is Professor Philip Koopman, who's Associate Professor, Electrical and Computer Engineering at Carnegie Mellon University. His research interests focus on self-driving car safety and embedded systems. Welcome, Phil.
Thanks for having me on, Gill.
Yeah, thanks for doing this. So it's a topic of great interest to me. So I want to start with one of your papers, Redefining Safety for Autonomous Vehicles.
Are you going right to the heretical paper that gets everyone uptight, right?
So you say here, existing definitions and associated conceptual frameworks for computer-based system safety should be revisited in light of real-world experiences from deploying autonomous vehicles. Current terminology, you say, used by industry safety standards emphasizes mitigation of risk from specifically identified hazards and carries assumptions based on human-supervised vehicle operation. So before we get into the details of this, Phil, so autonomous vehicles is a very broad term. Would you consider an aircraft to be an autonomous vehicle?
It might or might not be, depending. The paper is about ground vehicles, but I think the concepts apply to air vehicles. So an air taxi that has no pilot, for sure, is an autonomous vehicle. And if there's a pilot watching the autopilot, it gets into shades of gray. And the paper isn't really concerned about that. It's more saying there's been a sort of a creeping increase in the control authority of autonomy. And this is the boiling frog analogy, right? And then we're going to wake up one day and find out we're boiling. And taking the person out of the driver's seat or out of the cockpit or out of the control room is the thing that just sort of reveals all the slow degradation to the utility of the definition of safety that's been happening. It's been happening the whole time, but once you get rid of the person, you just can't ignore it anymore.
Yeah, so our scope is really terrestrial autonomous vehicles, let's call them.
Let's look at completely autonomous. There's no human driver, there's no human pilot, not because it only applies to that, but because it helps clarify what the issues are.
Right, okay, so we have a lot of data on human-driven terrestrial vehicles for a long time. We have had them many, many decades now.
Yeah.
And autonomous vehicles are sort of a recent innovation.
Well, not that recent. No, I've been doing it since the 90s, but
the 90s,
people haven't been seeing them on their local city streets until the last few years. That's for sure.
Yeah, I know Carnegie Mellon has been sort of on the forefront of this idea.
Yes. I started doing self-driving car safety in the late 90s as part of the CMU, one of the 3 CMU teams working on that technology.
Yeah, I was going to say, Phil, that we have a electric vehicle CEO in the US who seems to think that he invented artificial intelligence. Nobody has told him that AI started with the advent of computers in the 60s.
I took an AI course in 81, I think, but it wasn't neural nets.
And so we have had these ideas for a long time. We now have really powerful computers, very cheap memory, and we can embed them. And this is sort of what you focus on your research on modalities that couldn't take them before. So we can, now take a lot of data, analyze it, and make some decisions. So I want to ask you. So I don't have a deep background in this field, but I want to ask you. My intuition is that if I look at an electric vehicle today, there's a lot of talk about deep learning and machine learning and all of that stuff. But I would imagine there's still a lot of rules-based stuff in there, right?
Well, it depends who you talk to. Some of the companies say we can do end-to-end learning, and it's just one giant black box. You put the camera in one side, you get steering commands out the other, and you can get it to kind of drive that way. And some people say they can get it to drive really well that way. And there's other teams, most, not all, most of the commercial teams are using it more tactically. There's a chunk of machine learning here and another chunk of machine learning here, and they're putting some rule-based stuff in the middle because it can be hard to get machine learning to figure out stuff you don't see very often, or there are constraints that maybe human drivers drive sloppily in some way, and that's not actually what you want. So it's a matter of who you talk to. And some companies are convinced end-to-end machine learning is the one true path, and other companies are not doing that, and we're going to see. But most of them are not really considering safety that deeply, if you'll forgive the pun, when they do this. They're mostly worried about, can we get it to drive? And they think that safety is not crashing into things, which is part of safety, but it's not all of safety, not by a long shot.
Yeah, yeah. And so, you know, a system is only as good as the weakest link. And so if a company is saying we have some rules-based stuff in between our deep learning, machine learning stuff, then we have introduced humans into the software, and humans are notorious for making mistakes, much worse, I would argue, than machines. And so in a sort of a system that has rules and deep learning, I think your risk is still the sort of the same that emanates from the human errors, right? Is it true or no?
Well, nobody knows how that's going to turn out. Rules-based systems are subject to human error in not thinking of rules or putting the rules in wrong.
Yeah.
There was a recent Waymo crash into a telephone pole that, from the information they released, was somehow telephone poles got tagged as it's okay to hit. And that sounds like a human error to me. We don't know how it happened, but it wasn't that telephone poles, all telephone poles hitting them. Yeah, no big deal. And apparently this is the first time a telephone pole had been in a place they wanted to drive, and so it hit it. That sounds like a pretty classic software bug to me. Now, we don't know how it happened, but machine learning also makes mistakes. They're just sort of different mistakes. For example, if machine learning has never been trained on people wearing yellow, then you're going to have trouble that it won't see construction workers or school crossing guards in yellow raincoats. And that's not hypothetical. I've saw that behavior from a vision system. So everyone says, oh, people are terrible drivers. Actually, people are better than you might think. One fatality per 100 million miles. I mean, I really wish it were better. And a lot of those are drunk drivers. I get all that, but that's still pretty impressive. That's a lot of nines, 99,999,999 miles without a fatality. That's a lot of miles.
Yeah.
And guess what? Computers make mistakes too. So we're going to see how this turns out.
Yeah, I saw something, Phil. I can quite remember. I saw an electric vehicle getting thoroughly confused following a truck that has a cow, in the back. So the truck is carrying.
There was a video of a truck hauling trees and a robotaxi going crazy behind it because it didn't know apparently because it didn't know what to do with the trees. There's pictures of people on the sides of cars getting tickets for jaywalking from stationary cameras. All these kind of stories happen. They've been happening for years.
So that's sort of interesting sort of thinking about universality of these systems. So I grew up in India. Cows traveling back of the trucks is a common sight
Sure.
in India.
Hey, we had cows in my backyard when I grew up. I get it.
And it's not the case in the US, at least as far as I know. And so if you train systems based on some sort of geography or a grid that we believe the machine is going to get experiences from, then it's not necessarily universal, right? We can really take it across the world, possibly, right? Is that a problem?
Oh, not even across the county sometimes. Because I went to an inner city school, but we had cows in my backyard. So if you trained on the city, you weren't ready for around my place. That's true. Let me put it a different way. The limit. So this is, I'm talking about redefining safety, this paper, but we're sort of talking about the traditional part, and there's a bunch of other parts we should get to. But the traditional part, the challenge to safety, the big challenge to safety for all these machine learning based systems of any type, including driving, is that you have a long tail, or I would assert it's a heavy tail, which is actually worse, distribution. And so, you have the common things in the middle, and you have the tails out to the side, Gaussian curve, right? Except it's not Gaussian, it's worse. But think Gaussian curve, you got the tails. And the problem is these things learn by example. And so if you show them a set of examples that has a Gaussian shaped curve, then you're not going to have many instances of things out on the tails. and it's not going to have enough data to learn. And so when it sees one, it's just going to guess. And the issue from a safety point of view is that we're back to the 100 million, but there's only one bad thing in 100 million. Statistics aren't particularly good about talking in 1 part per 100 million, and the machine learning is all statistics. And so when you talk to a machine learning person, they'll say, well, 99% is really cool for machine learning. And if you're looking for movie recommendations, a 99% hit rate on movies you like is
good enough.
It's better than good enough. It's great. 90% is still pretty good, right?
Yeah.
And so when you use the technology for stuff like that, it can be really useful. But if you're saying, no, you have to be 99 point, it's like 9 nines or 10 nines or 11 nines, depending on 9 nines per hour, some number like this. Statistics just don't get you there. And in particular, if there's one crazy thing that happens per every 100 million miles, and you need 1,000 examples of it, what's your plan to get those? And people say, all right, we'll figure it out. It happens. We'll put it in a simulator. We'll synthetically create some data. Okay, cool. But you still have to make sure you know all the many, many, many things that happened at 1 per 10 million, 1 per 100 million, 1 per billion. And there's so many of them, it's hard to find them all. And any one of them could kill someone. I mean, so that's why it's hard. It's you have rare events with high severity dominate safety because it's all about the losses, not about the wins. And how do you collect enough things to train it on of things that almost never happen, things you'll never see in training, and things that the biggest robotaxi company now, Waymo, I think they just said they had 14 million miles. Well, 14 million miles, okay, 86 million miles to go to 100 million, and you actually need 3 times that for 95% confidence with no fatalities. It's a numbers game in this. The numbers are stacked. The numbers deck is stacked against the companies.
Yeah, and it gets more complicated, as you say in the paper, that there is an interaction between human and machine as well. So to the extent that we haven't gotten to, I don't know what's called level 5 autonomous vehicles.
Don't even go to the levels. That's a waste of time. Don't even do the levels.
Okay. So what I mean is that there's no human in the vehicle, and go ahead.
Well, let's split that. There's two kinds of automated vehicles. There's the kind that counts on a human driver being there. I call that supervised. And there's a kind that says, no, there's no driver in there. That's autonomous. The supervised is tricky because the human computer interaction is tough. People are terrible at paying attention to boring things that almost always work. But we're back to the numbers game. Well, if it only tries to kill you once every 1,000 miles, you're probably not going to be ready when it happens. Right. So that's the core problem there. For fully autonomous, it has to be right every single time because there's no human to bail it out. And so for the two technologies, those are kind of the hard parts.
So if the human is in there, and I'm thinking there was a flight, I don't know if you remember, from Brazil to Spain, I believe, that crashed in the Atlantic, and it was a severe storm. And as you know, this thing called
this is the Air France flight at the equator.
Air France flight, yeah,
right, okay.
So there's this thing called disengagement, as you know. So the machine says, "Hey, I can figure this out. You guys take over." Yeah. And the guy's sitting there, having a glass of red wine, saying, "Hey, I didn't plan to take over, so now I have to take over." And when the human is forced into taking over, they tend to make a lot of mistakes. So I think ex-post analysis of that scenario was that if they didn't take over, they might still have been okay. But the humans taking over actually crashed the flight.
They didn't have the right situational awareness, and they hadn't been trained on the particular failure about loss of airspeed sensors and all those things. Yeah. So for cars, again, this is the ones that count on the human driver. So we're not talking robotaxis. We're talking about the other ones, the ones sort of in the middle, the Teslas and the Ford Blue Cruise and the GM Super Cruise, those kind of things. What you have is a car that works, and in some of these cases, it can work pretty well for quite a while. And the driver is told you have to pay attention the whole time. And we've known since the 1940s, people are terrible at that. On a good day, someone who's a professional trained, they know you're watching, they're doing the best they can. After about half hour, they just can't concentrate. You just can't do it. That was a study with radar operators in 1947. We've known this forever. And the 1990s, when I started getting involved, there was talk after talk at these meetings about when you take away steering from the driver, they're just not going to be able to pay attention. And so we've known this, and then the robotaxi folks had to figure this out again for themselves a couple decades later. And I'm like, yeah, that's no surprise. We knew that, but they found that Google employees were falling asleep when they were told to pay attention. And you can blame the people for not taking it seriously, but that's like trying to make water flow uphill. This is how people are wired. This is what people do. And trying to deny that is not going to get you safety. People don't pay attention. So you combine that with, oh, and by the way, when something goes wrong, it's a life-threatening crisis. You've got a problem. So there were some studies after 3 Mile Island about human factors in nuclear power plants. And their study population was highly trained nuclear power plant operators. I've met some of these guys. I used to drive a nuclear submarine, so I knew a lot of the guys who worked in engineering, and these guys really know their stuff inside out. And so that was the population. And what they said was, if I'm remembering the study correctly, this is from the late 80s after 3 Mile Island, what the study found was that if you have, oh my goodness, everyone's going to die, loss of primary coolant, accident, something real, just all hell breaks loose. Your probability of someone doing the wrong thing in the first minute is nearly 100%. They're so freaked out, they're just going to get it wrong. And I recall training, I had some training that when all hell breaks loose and there's an automatic engagement system, the training is to let the automatic stuff do its thing, take a deep breath, collect your wits, and then do it. Well, if your car just steered you into a tree, you don't have time to do that, right? And so, anyone who expects a driver who's been, half awake and sort of just like, yeah, it's got it, and an hour later to all of a sudden jump in and in a fraction of a second swerve away from the tree that it just swerved them to, that's just not going to work out.
Yeah. Yeah.
Now they're doing driver monitoring. They're saying they have some technology, and we'll see. Maybe it can prevent you from getting in that sort of groggy state, but this is the big challenge for those kind of vehicles, is making sure the driver's really there and ready to dive in when you need them to, in spite of the fact that people are wired to not be good at that.
Yeah, I worry about that a little bit, Phil. So my thinking would be that if you introduce human into the modality, I would think that you're going to get suboptimal outcome. In other words, I'm really keen on getting something that doesn't involve the human, because I have very low confidence in humans. Being able to, as you say, jump in at critical points and make the right decisions, because they're sort of switched off in these types of modalities, I think, right?
Well, there are two ways to look at this, and people in the industry look at it. Well, there's three ways people in the industry behave, one of which is not good. The one that's not good is, tell you what, we're going to put in a computer that's not the greatest driver, and we're going to blame the human when there's a crash. That has not been working out well for us, and we should stop doing that. All right. Yeah. There's two others, and the industry loves to use the narrative of, well, humans are terrible drivers, so blah blah blah. But making them jump in at the last minute doesn't help. And all it does is then you get in a situation where the automation gets credited with all the saves and the humans get blamed with all the crap. And that doesn't drive safety. What that drives is lawsuits that blame humans. That's what that drives. There are two ways you can make it better, and it's not clear to me which is going to win. I think the human one's going to win, but we're in the next 10 years, maybe 100 years from now, who knows? But next 10 years, I think maybe the human's going to win, but we'll see. The first one, without humans, people say, well, get rid of those humans because they're all full of errors. And that narrative worked for a while until we saw robotaxis making the same mistakes that humans make for different reasons, because they're not very smart, and they get confused pretty easily by things they haven't seen. And guess what? They have software bugs. There was a robotaxi that ran into the back of a bus because it had been trained on regular standard buses, city buses, and it had not been trained on the bigger buses that have the joint in the middle, the buses that bend in the middle.
Oh, yeah.
And so it ignored the back half of the bus and just ran into it. The sensors saw it, didn't know what to make of it, so it just pretended it wasn't there and ran into it. I mean, Humans run into the back of a bus because they're texting. They don't run into the back of the bus because they decide it's not there when they see it, right? So it's a similar, to be clear, humans make mistakes that look the same, but they're making the mistakes for very different reasons. So we don't know how robotaxis will go. Now there's another one. I promised you 3, so there's a third one. The third one is you have a human driving, and the computer's job is not to take over the driving. The computer's job is to jump in when the human makes a mistake. Computers are really good at that. Computers are really good at instantaneous response to pre-programmed things. And so you're approaching another car, and if you do the math, you can find out that your tire limits are 0.7 G deceleration. That's a pretty standard number, okay? And you're at the point where if you hit the brakes at 0.7 G, you're gonna miss it by an inch. What say we have the computer dive in and apply the brakes for you, right? And that is called automatic emergency braking, and that is statistically dramatically reduced crashes when that feature's there. Okay, so we're not asking the computer to do with weird things. We're asking the computer to do pre-programmed things. We're asking the human to deal with a weird world, and we're putting the computer as a backup in case the human makes a mistake. And right now, that is, if you want to improve road safety, that path is your best bet for the next 5 to 10 years for sure. We'll see about robotaxis, but right now, automatic emergency braking is saving more lives and will save more lives for the next years than robotaxis will for sure.
Yeah, I think we have had this, what's it called? The sort of the intelligent braking system, like, it can recognize if there's a car in front of you and you can sort of set the distance.
Automatic emergency braking. Yep. There's the adaptive speed control, which sets the distance, and automatic
cruise control, automatic, sort of cruise control.
There's adaptive cruise control, which sets the distance, and that helps keep you out of a situation where you don't have time to brake. And there's automatic emergency braking, which is if you get closer, so close, and the guy in front of you slams on the brake, it'll help bring you to a stop. Yep. And those are in a lot of cars right now. They're not perfect for sure. They could be better, but the theory is that if the human already made a mistake and you're preventing the crash, you don't have to be perfect. You just have to do better. You just have to statistically reduce the harm.
Yeah, I mean, it's a different direction. It's disappointing. I'm still sort of holding out for I don't have to drive anymore idea.
Well,
but in the interim,
that's happening a little, but people keep promising 1 year, 2 year horizons, and it's a 20-year problem. It's a 20-year problem. And even if they solved it tomorrow, it'd be 10 years before we had that many cars, because the average US car is 12 and a half years old. So just do the math on what the fleet changeover time constant is going to be. It's going to be more than a decade. So this is going to be a long time before robotaxi technology matures enough to save people, and even longer to have enough vehicles on the road that it moves the needle.
And then there is sort of fleet intelligence and fleet communications. So it's almost like if you go all the way, things could get really good. In other words, if everything is automated, autonomous vehicles, and they're communicating with each other, then I would suppose the system would be much more optimum.
Well, one hopes, but it turns out it's really hard to build that kind of system. It's really hard.
Yeah. But that's what people have been, sort of promising, right? So your thinking is that we won't get there for a long time.
This is a multi-decade problem. Having computers driving cars instead of people driving cars is a generational technology. Everyone's promising it'll be in 5 years. Why? Because venture funding requires 5-year return on investment. Okay, let's be direct about what's going on here, right? And there are robotaxis driving around in a couple cities, and that is incredibly impressive, but it's still a science experiment. And so expect this to take years. Don't expect this to happen overnight. And they're still having teething pains. The technology is still maturing. So I think it's really cool, and it's really great that the technology is maturing. They say it has the promise of saving lives. I'm not disagreeing with that, but it's a 10, 20-year promise, not a next year promise. I just did some math that if you look at the Waymo said they have 50,000 rides a week. But if you do the math, it's 20 years to get statistical confidence on fatality rates. Okay. So, that's not saying anything bad. It's just saying if you read the propaganda they put out saying we're busy saving lives, the answer is, yeah, 0.05 of a life right now, maybe. They're it's just going to be it's just going to take a long time, and that's okay. We should be patient. What we should not do is forego other methods of improving safety, saying, oh, we don't have to improve our roads, we don't have to have better driver training, we don't have to deal with drunk drivers because the robotaxi is going to save us. Well, it's not going to happen this decade.
So I want to go into that, Phil. So you have another paper here, a reasonable driver standard for automated vehicle safety. You say here, current safe enough autonomous vehicle metrics focus on overall safety outcomes, such as net losses across the deployed vehicle fleet using driving automation, compared to net losses assuming outcomes produced by human-driven vehicles. So, before I read your papers, I was of this sort of view. I'm a utilitarian, and I would say, yeah, just look at the aggregate data. If technology X, it has a lower loss of human life, then it's the status quo. I would opt for technology X, but it's a much more complex question than that, right?
It is, and this is actually the intersection of the two papers. So I'm glad we're at this point in the discussion. So let me try and sort of sum up the big picture, and then we can dive into this. Engineers love to be utilitarian. That just is like trained into us, and I get that. Believe me, I get that because I'm trained as an engineer too. All right, it's not a problem. All my degrees are in engineering. I get it. Okay, so I want to take you through a fairly quick discussion where hopefully I'll make some points, and everyone watching can say, oh, I hopefully they'll say I get it, or they can say I'm an idiot. Whatever. We'll read the comments and see how that turns out. Okay, but the first one is people say, and I'm going to use round numbers, and I'm going to say things that are hypothetical for the sake of argument. So nothing I say is intended to accuse any robotaxi company of having a certain failure mode. This is just, we're doing thought experiments. I put that disclaimer up because I want everyone to understand this is thought experiments, okay? In round numbers, this is a real number. Really round numbers, it's about 40,000 deaths on US highways every year. That sounds like a lot, but it's because we have trillions of miles. We do that, it's just a lot of miles.
So how many miles, do you have an approximate number on how many miles are driven in the US?
I remember it's trillions, but it's 40,000. It's 40,000 fatalities from our home audience with a calculator. You can test me. It's 40,000 fatalities per year, and it's about 100 million miles per fatality. So do the zeros, right? It's a lot of miles, right? Okay. And we'd love that to be lower, but people say, oh, that 40,000, that means humans are terrible. It's like, no, it's just that many miles. It's very simple math. Okay. So, but let's look at the 40,000. Let's say you could take the 40,000 and make it 10,000, right? From a purely utilitarian point of view, you just saved 75% of the people. That's got to be a win. Hey, you know what? If we went from 40,000 to 10,000, I'd be delighted. But it turns out, especially non-engineers are going to have problems with that. But I want to convince the engineers to also have a problem with that. All right. And it's not that it's bad to do that. It's that there are more constraints. It's not purely an optimization problem. It's a constraint satisfaction problem where one of the constraints is that number needs to go down. For sure, you would not want the number to go up, I hope. Some people say, well, it's okay if it goes up because it'll go down later. That's a whole different philosophy, and we're not going to go there today, okay? We do not need to have an opinion about that, but someday it needs to go down. I'd prefer it to be immediately. All right, that's constraint number one, it has to go down. Number two, let me just give you a hypothetical. What if it goes from 40,000 to 10,000? And I'm being extreme to make a point. What if all 10,000 are a child on the way to school in a school crosswalk who gets run over? All 10,000. Is that going to be okay? Do you think the industry could survive that? Do you think that people would be okay with every single victim being a child? Yeah. I don't think that's going to work. I don't think that's going to work, right?
Yeah, the only thing I'll say, Phil, I mean, you know more about this than I do. The only thing I'll say, if that's the case, we can fix that problem because there's so much data why that's
Well, we
happening, right?
hope we can fix the problem. What if every victim has dark skin color? Because that's a known problem
Mm,
with recognition, okay? What if every victim is a pedestrian and everyone in a vehicle survives and everyone who dies is a pedestrian, and net, it's twice as many pedestrians as die today. That actually is not that much of a stretch. It could certainly turn out that way if we're not careful, all right? So
yeah.
the point of this is not to tell you what was reasonable to happen. It's to make people think and say, there's more to it than the net reduction. There's also a component that it's not okay to disproportionately harm people who are vulnerable to get
Right.
the net reduction. I mean, if it's, I did the kid just to make the big point to get people thinking, right? But the more likely one is it's going to be pedestrians or some category of vulnerable. What if it's people in wheelchairs? What if it's whatever, right? There's going to be some vulnerable population. If they experience increased risk
Mm,
for the benefit of not even them, for the benefit of other people who are riding around in these robotaxis,
mm.
that's going to be a social issue. That's not going to be okay.
It's almost like a subsidy. You're
Well,
subsidizing one part of the
yeah,
population. Yeah.
and you know, uh, that's that would be pretty bad. I think we would have,
Mm,
it would. I think we would have some issues. Now, I'm not saying it has to turn out that way. What I'm saying is it's almost certainly socially unacceptable for it to turn out that way. And the reason I say that is people say safety is purely utilitarian, reduce the amount of harm. Well, no. One of the constraints is net harm is no worse and probably should be reduced. But the other one is you're not allowed to disproportionately inflict harm on vulnerable classes, especially if they're not betting from the technology.
mm.
And this gets into the, is it okay to put a chemical factory and poison everyone in the city near the chemical factory so the other side of the country can have really cool stuff? It's not so different, right? It's a similar kind of issue that
Yeah.
it's not okay for some people to pay a price for others that's disproportionate to the benefit they're getting.
So I don't know if this is in your research, Phil. So let me ask you. So the problem is sort of multifactorial in the sense that you have to think about city planning. I know that Netherlands, not your Holland, Michigan, but the country in
It might,
in Europe.
the audience didn't hear that. My last name is Koopman. It's a Dutch name because my ancestors are from Holland, Michigan. That's right.
Yeah, so I know Netherlands has sort of cities now that
Mhm,
does not allow vehicles at all. So
mhm,
these are walking cities.
mhm.
So do we have to solve this problem more holistically? Meaning, yes, get fully functioning autonomous vehicles, but there are going to be places where vehicles don't go at all. I mean, there's a city
Well,
planning problem here too,
that's
right?
one way to solve it. And
Yeah.
so as the safety guy, I'm not telling you how to solve it. We can have discussions about urban planning, but that's sort of a bit of a topic. I'm just saying you can't ignore that disproportionate harm on vulnerable populations is an additional constraint to safety. So traditionally, when you read the functional safety standards, if you look at decades worth of safety, it all has the flavor. There's nuances. Lots of safety folks know more than this, but if you just do a plain reading of the definitions, it's all about we're going to reduce risk. And what it doesn't talk about, but what it needs to talk about is we're going to reduce net risk. But in
Yeah.
addition to reducing net risk, we have to also make sure there's no disproportionate risk on populations who it should not be imposed on, usually vulnerable. So that's number two. There's a number three. And number three is safety standards historically have stayed the heck away from legal stuff. It's like,
Mm,
oh, that's the lawyers. We're not going to do that. We're engineers. That's the lawyers. Okay. And that's the issue of liability. And liability is a similar constraint because what you would do if you have a regular car with a human driver, all the conformance with laws is delegated on the human driver, and other than governmental equipment regulations, I'm setting that aside. But behavioral, don't run stop signs. Don't run
yeah.
stop signs was on the human driver, and if you ran a stop sign, it's the human driver's fault. But if you take the human out of the car, guess what? The computer driver has to conform to the laws too.
Mm,
And there's without getting deep into it, this is the second paper. There's this concept of duty of care, that human drivers have a duty of care for the safety of everyone else on the road. And if you violate the duty of care, you're negligent, and there are potential criminal penalties or civil penalties. And if you take the human out, now the computer should have a duty of care to all the other road users equivalent to a human driver. I didn't say perfect, but if a human driver would not have accelerated toward a person in the crosswalk and hit them, then which would be negligent probably. And, I'll bet that one's negligent unless there's some crazy extenuating circumstance, like it got shoved through the intersection by a truck hitting it, or, something. Set aside the crazy stuff, right? You should not be accelerating into pedestrians in a crosswalk. In California, that's against the road rules. And a computer should be held to the same standard as a human. Well, that's an additional constraint on safety. That safety is reduced net harm, or no worse net harm. Number one. Number two for safety is you have to make sure that you're not disproportionately putting risk on vulnerable populations, especially ones that don't benefit. And number three is you can't act in a negligent manner. Now you could say, well, these all sound good, but let me give you, again, hypothetical, but not very far-fetched. What if the robotaxis keep getting hit from behind at stop signs? This has been going on for years. Because human drivers are impatient, they hit them from behind. It's always blamed on the human driver following. Let's just take that as given. Let's say you're a robotaxi company, you decide to not stop at stop signs. You're going to roll through stop signs. Yeah. Why? Because net safety is improved by not getting hit from behind. And you say, I'm only going to roll through stop signs where there's no pedestrian in the crosswalk. And the day comes, you don't see a pedestrian, you roll through the stop sign, but the pedestrian is there and your perception failed and you hit the pedestrian and killed him. Right. Guess what? If a human driver did that, that might be negligent homicide, depending, right? Or whatever the equivalent state law is. The lawyers get, all detailed about this. But, you could have done something criminally negligent programmed into the car. And if there's no human there, I'm going to say that's a problem. You should not be designing to break the law on purpose. That's an additional safety constraint. And now people say, but you have to break the law sometimes. Yeah. But yes, there's a tree down and you go around the center line to get around the tree. I get that. But if you're breaking the law and you make a mistake, it's your fault for using poor judgment. And computers are going to have to deal with that. So that's an additional constraint on safety, that if you're breaking road rules, you're taking an extra obligation for safety and saying, oh, I've gone 100 million miles without killing anyone. You would never say a person gets a free kill because of that, right? But if you say, I went 1 billion miles and didn't kill anyone, so the fact I broke the law on purpose and killed someone, I get a free pass. Well, it doesn't work that way for people. It shouldn't work that way for computers.
Yeah, so what I'm thinking, Phil, is that autonomous vehicles will work if we can take all humans out. It's not the autonomous vehicles.
Well, and that's not clear. It's not clear. They're still going to have autonomous vehicles are making the same mistakes people make. Go read the newspaper. We have autonomous vehicles hitting buses. We have them hitting telephone poles, both of which were avoidable. We have them driving into wet concrete in construction zones. We have them ignore road closed signs and driving through construction zones. We have them running over fire hoses in emergency response things. They're actually making the same mistakes humans make for different reasons. Technologists love to say, if we got rid of those humans, the world would be perfect. But you got two problems. The first is perception of the outside world has error. It's not perfect. And so because the perception's imperfect, your world model differs from the external world, and you'll have mistaken judgments. That's the first one. The second one is, who builds these machines? People. Do people make mistakes when they build machines? Yeah. So the world, I know engineers love to think if we got rid of the humans, the world would be perfect, but you can't get rid of the engineers. And you know what? Stuff breaks.
Remain. And they're the problem makers.
Software doesn't exist. Perfect software doesn't exist.
And so I want to go into the legal aspects of this a little bit, and it's part of your other paper too.
Yeah.
So there is a question. So you argue here, if I understand this correctly, Phil, things have to be looked on a case-by-case basis. And maybe the comparable thing to think about what a reasonable human driver would have done in a specific incident, and then compare that to what the machine has done. And that gives you some information as to what the legal, issues, liabilities, and also all sorts of things around it. Now, what I don't quite understand is how would you define a reasonable human driver?
Oh, that's a great question. That's a great question. So let me summarize to make sure everyone's sort of caught up with us. The idea is drivers should not be perfect. So computer driver is the computer driving the robotaxi for our purposes. They should not be held to a standard of perfection, because the things I said about safety don't require perfection. They just require it to meet some various constraints that are socially required. Okay, so well, how should you set it? Well, you might say we go statistical, but now you have liability, you have this vulnerability, road user thing. So that's not enough. Instead, what we're going to do is, for the liability thing in particular, you want to be reasonable. And reasonable is a human driver who does not make stupid mistakes.
But stupid is very difficult to define.
Well, if you're texting on the cell phone and you're not looking out the window, would you say that's a reasonable driver? I'm going to say no. Okay.
Well, I mean, in aggregate today, that might be, well, it's not a reasonable driver,
it's
but
not
a common
an average driver. It's not an
Yes.
average driver. It's a reasonable driver. It's this legal principle. By the way, I'm not a lawyer, but I've hung out with them enough. I'll give you the general ideas. Go see a lawyer if you really need the details. So reasonable person is this legal principle of a human who's not superhuman. They're not expert. They're ordinary, with an exception that they don't make avoidable mistakes.
Yeah.
So you've heard of like an unforced error. A reasonable person doesn't make unforced errors, but they can make forced errors.
Yes.
Right? The proverbial boulder drops 1 meter in front of your car and you're going 60 miles an hour. Guess what? You're going to hit it. There's just no way around that. And that's a reasonable driver. Reasonable driver was moving toward the brake, but probably didn't even have time to hit the brake pedal. Yeah. Okay. Or somebody runs out on the road and your foot's on the brake and you're decelerating, but you hit them because Sir Isaac Newton had something to say about this, and people have reaction times of hundreds or thousands of milliseconds depending on their age, and as long as you did what any reasonable person could be expected to do, it doesn't mean you're superhuman. It just means you acted to the best of your reasonable ability. Then you're not negligent. Okay. Now the thing that just gets engineers just tangled up in knots beside themselves is they want a formal specification for what it means to be a reasonable person, and that doesn't exist, okay?
Yes.
And I had this discussion with a lawyer co-author. I have Bill Wyden is my co-author on, I have law journal papers. I never thought that would happen, but I co-authored them with an actual law professor, all right? So that he kept me straight. And we had this exact discussion. It's like, well, Bill, it sounds like a subjective standard to me. He said, no, the courts consider it, the law system considered it as objective because there's a degree of repeatability. If you ask 100 juries, if you say 100 juries, well, this person killed someone because they were looking at their cell phone and now out the window, was that a reasonable driver? 99 or 100 of the juries are going to say that was not a reasonable driver. They should have been looking out the window, okay? Not average. I know people misbehave. And when they misbehave and they do harm, they're open to civil and criminal penalties, right? That's, there's consequences.
So it's sort of application of societal norms on the driver.
Well, it's societal expectations. You want to call them norms, but it's not norm in the average behavior. It's the societal expectation, if you want to look at it that way. So norms in that sense. I just want to make sure, yes, that is the usual definition of societal norms, but I don't want to get tangled up and people misunderstand, right?
Yeah, so I'm not a lawyer either. So I quite like this. So what you're saying is that there's an expectation of an autonomous vehicle's behavior.
Well, I propose this expectation. It should be that they're no worse than you would expect a human driver.
No worse than what you
would expect from a reasonable human driver. Reasonable human drivers don't drive drunk. They don't look at their cell phone, right? They're well-behaved who's not making unforced errors, right? That's what, so it should be, the bar should be set there.
So that's a
And
standard.
that exactly conforms to saying they're not negligent. So reasonable human driver is the standard for human driver negligence. And we're just saying computer drivers ought to be held to the same negligence standard as human drivers. Now, computers don't drink. Famously, everyone says, but computers don't drink.
But we don't know that.
They make mistakes that look like they're driving drunk once in a while.
Yeah.
And so how do you solve that? What you say is, well, I'm going to pretend I can't see the driver's face and I don't know the blood alcohol. I'm just going to look at what the car did. Yeah. And if by looking at what the car did, I would say that driver were behaving recklessly and negligently or being a jerk or whatever, and it led to a crash, I'm going to say the computer driver is negligent because we would have said a human driver is negligent. A human driver runs a red light and kills somebody. There was an autopilot case where this happened, that the autopilot ran the red light and the human driver wasn't paying attention. He killed 2 people, and that was negligence, okay? And they said he should have been paying attention. Well, take out the human. If a robotaxi runs a red light and kills 2 people, then that should also be negligence the same way. Why would you have a different standard for the behavior?
Yeah, I quite like this, Phil. I haven't thought a lot about this.
So that was the point, Gill. That's the point of our conversation, to try and stretch.
But I want to ask you, so we have talked bad about humans on this show, but one thing humans are good at, I would argue, is sort of one-shot learning. They don't need a lot of data, right?
They're great in improvising. They're not perfect, but they're amazingly good. So humans avoid a lot of crashes. Roads aren't safe because humans are great drivers. Roads are safe because humans are really good at compensating for other people's mistakes. And what's that box in the middle of the road? And humans aren't perfect at it, but they're amazingly good at it.
Yeah. So do you think machines will get there? We can get, very large amounts of data and train them and all of that. And we know that is very brittle because you're always going to find a case that is not in the data set.
That's right.
And then you're going to fail. So do you think we'll ever get to, machines being sort of one-shot learning?
That's the $100 billion question, right?
Yeah.
So they don't have to be perfect at it. They have to be better than a human, but we now know better than a human is more than just the net statistical. There's these other constraints, okay? But none of that requires perfection. So it's a question of, can you find a smart way to spend your money to get there? And the challenge is, back to the beginning, I said heavy tail's the challenge. It's that you will never run out of weird cases. So can you come up with heuristics that catch enough of the, can you get ahead of the tail that you're able to, if there are things happening once per million miles that you're having trouble handling, well, how many cars do you have on the road? And how often are those happening? And how often are you getting lucky that the bad thing happened, you didn't notice, but you got lucky, it didn't matter, and you noticed it and you fixed it before it has a chance to happen again. If you approach it that way, you may be able to do scaling. So the industry gets into trouble when it scales too fast because they get ahead of that frontier of exploration of the weird things. What I say is that they have a bunch of loose ends, and if they scale faster than they can tie up the loose ends, they're going to have a big crash. And it's hard to tie up the loose ends, and so you see slow scaling for the industry. There's a reason, and that's sort of the dynamic that's playing out.
Yeah. I don't know if this is new research, Phil, but I'm just thinking, so all the electric vehicles today sort of upload all their data to some sort of central area, and
not all their data. Nope. So the Teslas of the world only upload a very small fraction of their data.
And so that's what I would ask you. So do you think the Tesla, the electric car in Holland, one car, and an electric car where I live in Connecticut, they could have their own personalities ultimately? If they're not really sort of loading data and kind of getting heuristics back from the mothership, they could have different experiences, right? They could ultimately have different ideas.
You have to localize what you learn, for sure. The easy stuff about not running into things is moderately universal, right? The things you're not running into varies, but the local road customs in Pittsburgh, we have this thing called the Pittsburgh left, where if you're at a stoplight that turns from green to red, fortunately that's pretty universal. I'm sorry, from red to green. So you're at a red light, there's two cars coming at each other. You're at a red light, turns to green, and one of them wants to turn left. If the person in the other direction is a local from Pittsburgh, they're going to wait for you to turn left in front of them, which is totally against the driving laws. Okay, but they will get upset if you don't turn in front of them because they're being courteous. If the person is from out of town, they'll hit the gas and hit you. So now you have to decide what you're going to do about that.
Yeah.
And every city has their local driving customs. In Pittsburgh, they put chairs in parking spots, and you should fear for your life if you move someone else's chair out of the way and park in that spot. Not a good idea. Okay, and that's also against the law, but people do it. So every city has their quirks and has their customs and has different level of, they call it aggression of driving. That's the word people use. So what you learn in one city may be custom to that city, and that the challenge is how you can generalize from that. On the other hand, people go to a new city and they figure out the Pittsburgh left, maybe not the first hour they're here, but they figure it out pretty quick and they adapt.
Right. So
yeah.
This is the issue with deep learning, right? So we still need large amounts of data.
Yeah.
And by definition, that's going to be quite brutal. I mean, you just need one case that doesn't fit in.
But what humans have that computers, current artificial intelligence, quote unquote, machine learning, right? What we have that they don't have is we have general intelligence. We're able to reason. We're amazingly good at, I don't know what's going on, but I don't like the looks of it. I'm going to go to a safer state. And machine learning its Achilles heel is false confidence that it's absolutely sure, but it's really just guessing because it's data it hasn't trained on, and it's just guessing. Now there's certainly work on, they call it outage distribution detection, but that has issues because the dimensionality of the distribution may be one that you didn't even realize mattered. Like you say, well, if it doesn't look like people I've trained on before, if it doesn't feel right, I'm not going to know. But what if clothing color is what's different and you didn't even know clothing color mattered? Turns out it matters to training. Turns out, but if you didn't know that, you're not going to realize someone dressed in yellow is a person because it's not even in your model. I don't want to go too deep into this, but there are ways you can help these things know they don't know. How do you know what you don't know? It's hard for people. It's even harder for machines. Very much a research topic. Yeah. But people are really good at saying, you know what, this doesn't smell right. I know that I'm in over my head. They're not perfect. We're good at it. Now, while I can't give you the rigorous study, let me give you some anecdotal data to back up the intuition, okay? So if you have a 20-year-old driver who has really good twitch reaction times, right? They're great at video games. They're really, really fast. People say, oh, computers are faster than people. They can react faster, therefore they'll be safer. So let's look at people. If you have a 20-year-old driver and you have a 60-year-old driver, the 60-year-old driver is integer multiples safer.
Yeah.
There's a reason rent-a-car companies don't want to rent to anyone under 25. It's because
there is a reason insurance rates are different. Yeah,
that's right. Because up until 60, you're getting safer every year, and below about 30, you're actually pretty dangerous. Okay. And so people who say computers are quick, therefore they're safer than people, haven't looked at the people data. And my interpretation of that is it's a curve that just goes down and it goes up a little. By the way, the 80-year-olds aren't near as scary as a 20-year-old.
Yeah.
Believe it or not. Well, why is this? It's because being smart enough to say, that's a spectacularly bad idea, I'm not going down that road, outsmarts being able to react quickly when the bad thing happens.
Yeah. Excellent, Phil. I'm getting a bit depressed because I was hoping to get a fully autonomous car.
Well, you can go to San Francisco and ride in one right now, or Phoenix. Go have fun. So the autonomous stuff has already happened. It's happening. Yeah. It's going to continue to happen. It's not a matter of whether we can do it. It's whether we can do it at scale is the hard part.
At scale, yeah.
the scale is and everyone's like, oh, it's on the road, so surely by next year we'll have it. It's like, no. I've been working on self-driving car safety for 25 plus years, almost 30 now. And it's going to be another 25 years for the scale thing to work out. It's at least as hard. And so don't be depressed.
What are you guys doing there at Carnegie Mellon? You guys
should
have solved this problem a long time ago.
Well, it's that hard a problem. I mean, just don't be depressed. Just be thoughtful and patient. Okay. They're at what? Let me just do some numbers, right? Let's say they're at 99.9%. I'm just picking a number, right? But safety is 99.99999. I don't know, 7 more nines. And I'm fond of saying, hey, the machine learning is 99%. Let's revisit this. The machine learning is 99%. That's really impressive and it's great for some things.
Yeah.
Oh, safety? Yeah, 7 more nines to go. And by the way, each 9 is 10 times harder than the one before.
It's a different problem, yeah.
It's just a different, I made up a quote that's it's a play on, the 90-10 rule and the 90-90 rule. So the 90-10 rule is, we'll have a little fun, but the 90-10 rule is 90% of the 10% of the effort gets you 90% of the benefit, or the other, there's variations, right? There's the programmer's the 90-90 rule, which is the first 90% of the project takes the first 90% of the time, and the last 10% takes the other 90% of the time with a cost overrun of 1.8. Okay, that's a classic software. I've got the robotaxi version of that is the first 99% of the robotaxi takes the first 99% of the time.
Yeah.
And the last 1% of the robotaxi takes the other 99.99999% of the time.
Yeah. Excellent, Phil. Thanks so much for spending time with me.
Well, thanks for having me on, Gill. It's been a pleasure, and it's nice to have a general talk about the general principles. So I hope that I hope the audience sort of got an idea of what it's like to live in the robotaxi space.
Absolutely. Thanks so much.